Hello, AP Chemistry students. So this video is just a recap of what we were doing in class. So I told you I would go through the second example of each of our gas laws a little bit slower, so that if you need a little bit of help with them, you have a chance to hear me kind of talk through each of them again. So just remember, in this unit, we're just focusing on gases. One of the reasons why we have a whole unit just on gases is just how well we can manipulate gases and look at different relationships between variables. So the different things that we talked about in our earlier unit with how the particles are arranged in gases, gases volume can be greatly affected by pressure and temperature, how they have relatively low densities and so on. All these properties can really be described with four variables: pressure, volume, temperature, and then the amount or number of moles. So we talked in class about the ideal gas law, which we'll come back to at the very end of this video, where if we know three of those variables, we can use the ideal gas law to find the missing one. We're going to start, though, by talking about Boyle's, Charles, and Gay-Lussac's law, where we'll look at just two variables at a time. And what I mean by that is out of the four, two will be held constant. They won't change. And then we'll look at if I change, say, pressure, how does volume get affected? And vice versa. So I'm just going to focus mostly on the calculations, but I will try to give a little bit of the explanation behind it that you may have missed in class when we were going through it quickly. So the very first one was Boyle's law. This one focuses in on pressure and volume. And we talked in class about how as you change pressure, the volume is also going to change. So this graph here shows this inverse relationship between pressure and volume. So as pressure increases, you can see that the volume is coming down or decreasing. So that's the inverse relationship there. We also talked in class that when we were using our gizmo, we looked at pressure in terms of the external pressure, that the more external pressure you put on a sample of a gas, the volume is going to decrease. Just keep in mind that those gas particles in that smaller amount of space are going to be hitting the sides of the container more frequently, okay, which would also cause the internal pressure to increase. So just keep that part in mind if you missed that in class. So we know then that as pressure goes up, volume is going to decrease, or if pressure goes down, then volume can go up. And then Boyle's law calculation just focuses in on that pressure and volume. As long as the units for pressure are the same and the units for volume are the same, in this case for Boyle's law, we don't have to worry about converting anything. So we already did example 1 on here, so I'm going to look at example 2. So we have a sample of carbon dioxide that occupies a volume of 3.5 liters at 125 kilopascals pressure. What pressure will this gas exert if the volume has decreased to 2 liters? So we have our initial volume and our initial pressure, and then we have our final volume, and we're looking for P2. All right, so with this, just to point out of how this is different than, say, an ideal gas law situation, we have variables that are changing. So this is where we're looking at like P1 V1 versus P2 V2, and then we can use that Boyle's law. So using Boyle's law, okay, we're just going to simply plug in our initial values. So 125 kPa, 3.50 liters is going to be equal to our new pressure times its new volume. Okay, and just remember, it's because each of these are going to be equal to the same constant that we're able to set them equal to each other. Okay, and then from here, I would want to divide each side by 2.0 so that I have my P2, and then doing 125 times 3.5 divided by 2 and keeping to the 3 sig figs I have over here, I get 219 kPa. Okay, and if we look, this makes sense. If we look at our initial part, volume was decreasing, and we know as volume goes down, pressure must be going up. So our answer here does make sense with what we know about the relationship between pressure and volume. Okay? All right, our next one was Charles' law that we talked about. This one has to do with temperature affecting volume. One big thing with this one that we talked about in class is, remember, temperature has to be in the Kelvin scale, and that's related to the fact that in the Kelvin scale, it's related to the speed of the particle, or the average kinetic energy of the particle, which is going to kind of factor into this unit in a huge way that we'll come back to. There's a direct relationship between volume and temperature, so as temperature increases, volume is going to thus increase. We talked a little bit about this in class in terms of if pressure is being held constant, Okay, those gas particles are moving at a certain speed, okay, hitting the container with a certain amount of force. If I then heat this up, if I increase the temperature, they're now going to be hitting with a lot more force, okay, which in order to keep pressure constant, these guys now need to expand their volume, take up more space, okay, which would allow them to hit the sides of the container less frequently, which would then maintain that constant pressure that we're looking for. So again, think back to when you're going through these, how that factor, such as temperature, is affecting the particles, which is then resulting in the change, in this case, of volume. We talked about also in class about, because our temperature has to be in Kelvin, we can use this temperature conversion that's on your AP reference tables. So you'll be seeing me add 273 to any of our degrees Celsius. This little part that we talked about in class is just how we can get Charles' law from ideal gas law. If we rearrange these, we have our gas law constant, moles and pressure remaining constant. This would be the same value for a sample of gas. So this would be equal to a constant, and it allows us to set them equal to each other before and after a change in conditions. So because of that direct relationship, just remember, as temperature goes up, volume goes up. As temperature goes down, volume goes down. Okay, and same type of idea, like in this case, if we look at temperature going down, okay, you're at a lower temperature, those are going to be moving slower. They're not going to hit the side of the container with as much force. So then you're going to see them take up less space in order to maintain that constant pressure part. All right, so here we have Charles' law, where we're looking at that direct relationship. So volume over temperature, our initial conditions, setting those equal to the final conditions. Because again, both of these are equal to that same constant, which allows us to set them equal to each other. So for the second example of Charles' law, we have our oxygen gas. It's at this temperature of 40 degrees Celsius, which as soon as I see degrees Celsius, I'm going to make sure I remember that I got to convert it. So here is our T1. And then we have this volume of 2.3 liters. This is our initial volume. And it says, to what temperature should it be raised to occupy a volume of 6.5 liters? So here is my new set of conditions for volume. And again, I'm going to be looking in this case for T2. So again, how this is going to look different than ideal gas law soon is that we have a change of conditions, okay, and it's just focusing on temperature and volume. And again, usually some of these questions will indicate that pressure is being held constant, as well, to make it clear that we're dealing with Charles' law. So using our equation for Charles' law, V1 over T1 is equal to V2 over T2. Okay, I'm then going to input my data. So I have 2.30 liters. Okay, making sure that degrees Celsius. So I'm going to do 40 plus 273 would be 113. I'm going to make sure, because of this initial value, my adding the 273 constant, I'm going to keep to the temps place here. So that would be in Kelvin. And then we're looking for a new temperature after we go from 2.3 liters to 6.5 liters. Now I know that my volume is increasing, so I would then expect my temperature to be increasing. So let's check that. With this, you would end up cross multiplying. So your final setup would end up being the product of the 313 Kelvin times 6.50 liters divided by our 2.30 liters. Okay, and when you solve that and you're to round to 3 sig figs with this, you should end up at 885 Kelvin. Okay, and that would be my final answer there. Remember, no degrees sign with Kelvin, you just put the K, nothing else. Okay, so that was Charles' law. Gay-Lussac's law was that relationship between temperature and pressure in this case. We talked about, as you increase the temperature, if you have a fixed volume, that simply then is going to speed up the particles. They're going to hit the container with more force and increase that pressure that they're exerting within the container. So as temperature goes up, pressure goes up. But if we decrease temperature, those particles are moving slower. They're not going to hit the side of the container with as much force. So pressure is going to go down. And then this is our formula for Gay-Lussac's law that just focuses in on pressure and temperature. Again, it has this direct relationship, so you're going to see them above and below each other in the formula when we rearrange it, making sure that temperature is in Kelvin just like before. So with this one, apologize for this little part here, we're looking at number 2. So it says a gas has a pressure of 699 millimeters of mercury. So that's our unit for pressure at 313 Kelvin. What temperature at standard pressure? So with this one, we have P1 and T1. Okay, and then it says, what is our new temperature? T2, we don't know. at standard pressure. So you're going to see this in some of the homework where we'll say STP or standard pressure or standard temperature. So for us, standard pressure, which is, bring this up over here, you can see STP here on our AP reference tables. So this is your 1 atmosphere. Now 1.0 ATM, okay, and this is in millimeters of mercury. In millimeters of mercury, what's equal to 1 ATM is going to be 760 millimeters of mercury. We did that in the last set of notes too that you could look up. Okay, so that's going to be my standard pressure. So here for Gay-Lussac's law, I'm going to do P1 T1 over P2 T2. Okay, I'm going to fill in the values that I have, 699.0 millimeters of mercury, and then I have my 313 Kelvin. That's going to be equal to our 760 millimeters of mercury. Just remember that's a constant that I'm plugging in, so I'm not going to use that for my sig figs in just a second. And then I'm looking for T2. So when I rearrange for T2, I'm going to have my 313 Kelvin times my 760 millimeters of mercury divided by my 699.0 millimeters of mercury. So then when I go ahead and solve that, keeping that to the 3 sig figs, I get 340, which to make sure it reflects the 3 sig figs, I got to make sure I have that decimal point there. And this was in Kelvin. Okay, so it's another example of the Gay-Lussac's law that looks at that relationship between pressure and temperature. And again, if we check this, pressure went up, so I would have expected that temperature had gone up to result in that change in pressure. Okay, all right, so Boyle's law, Charles' law, Gay-Lussac's law, all of those together, if we don't hold one of those 3 constants, so we're only holding in this case the number of moles, if we change 2 of these, we can look at the resulting third. So you should be able to see how I have Boyle's law here, I have Charles' law in there, and I also have the Gay-Lussac's law in terms of all those, maintaining all those same relationships. Okay, so for this last one, which I know we didn't have a chance to really go through this thoroughly in class, so hopefully this will help you if you're having trouble with it. I'm just going to, again, go through and identify all the information that I have. So we have a gas that has a volume of 28 liters. It's a temperature of 45. So I'm going to just add 273 to that right away. So I get 318.0 Kelvin and an unknown pressure. So I don't know the initial pressure. And then we see a change in conditions. So again, I want to point out to you when we go to do ideal gas law, how this is different. Is ideal gas law, we're just going to have our set of conditions and we're finding the missing variable. Here we have a set of conditions that has now changed. So it's this changing of the variables. So it has its pressure volume increased to 34 liters. So this would be V2. Its temperature has decreased to 35. So if I do 35 plus 273, I get 308. If I measure the pressure after it to be 2, so after the change, what was that original pressure here? So again, I have pressure, volume, and temperature all getting affected. So I'm going to use that combined gas law with all 3. So I'm going to fill in my 28.0 liters. I don't know P1. Okay, T1 is 318.0 Kelvin. I'm going to set that equal to its new conditions. So I have 34 liters. I have 2 ATM. So that shows me when I solve this, my final pressure is going to be an ATM. And then 308 for my final temperature there. So when I go to solve this, P1 is going to end up being 318.0 Kelvin. So I'm just going to I'm kind of just cross multiplying across there, times 34 liters times 2 ATM divided by these guys, which would be divided by the 28 Kelvin, or sorry, liters, and divided by the 308. Okay, so I look through that, multiply that and correctly divide by those 2, and I'm going to round my answer to the 2 sig figs in this case. I will get an answer of 2.5 ATM. Okay, so that's an example of the combined gas law. Okay, we didn't do Avogadro's law yet, so I'm going to hold off on that, but I did want to show you just one more time the ideal gas law. So ideal gas law is basically like we're analyzing the gas. We have 3 properties of it, and we want to know the 4th in this case. So with this, we're going to be using this formula, which is on your AP reference tables. All the variables are defined for you down here. You're going to have some different R constants to pick from. For this unit right now, we're just going to be using this one here. And it's important when we do the ideal gas law that all the units match this because of that R constant being used. So when we look at the second example here, it says if I have 21 moles of a gas held at a pressure of 78 atmospheres, which is a really high pressure, and a temperature of 900, what is the volume of the gas? So when you read this, this is just giving you one set of conditions. There's no changing occurring. It just has three of the variables. It wants to know the fourth. So that's where I want to use my PV equals nRT. So I have moles, I have pressure, I have temperature, which is in Kelvin. Okay, this was an ATM, which is what I need it to be in, and is of course in moles. And then I'm going to be looking for my volume. So some students do like to rearrange this ahead of time. So if I'm looking for volume, I would have to divide both sides by P. So this would be nRT divided by P. Okay, so I'm going to fill in my 21 moles. And remember what I said in class, make sure you write down everything in the problem because that's what you're probably going to end up looking for your sig figs. R, we're going to use our 0.08206 meters times ATM over mole Kelvin. And then my temperature, 900 Kelvin. Make sure I include that decimal point there so I remember that has 3 sig figs. Divided by the pressure, which was 78 ATM. Okay, so that would be my setup in order to help me analyze for the volume here. And then when you plug that all in, and in this case, I'm going to put it to 3 sig figs based on, don't look at the constant. I'm looking at these three numbers. They all happen to have 3 sig figs. So my answer will be to 3 sig figs. That gas would have to have a volume of 19.9 liters. Okay. If you do end up trying out number 3, you should get 2.0 times 10 to the second Kelvin when you do that one if you want to try it out. All right, last little part, tips for solving that you might not take a look at on this last page. Again, as I've been trying to point out to you repeatedly, if there is a change in the variables, you have to use some version of the combined gas law. Okay, if just 2 of those 4 variables are having a change, then take out the one that's being held constant and look at just the individual gas law. Okay, and again, this one is the PV over T is equal to PV over T. If just one variable is unknown and the 3 are known as well as R and there's no change, we just analyze it using the ideal gas law and make sure all the units conform to R. And the ideal gas law is the PV equals nRT. Okay, so hopefully that helps you as you go to do the homework tonight. Remember to check over Classroom.